We live in 4 dimensions. 3 of the dimensions are familiar spatial dimensions. I can go from where I'm standing right now all the way to here, and I can walk exactly back to where I came from. But the 4th dimension we live in is time. And while we can go forward in time, we all know that we are not able to go backwards in time. But why is this so? What makes time different? Indeed, most equations in physics are symmetric in time. Whatever happens in one direction in time can actually happen in the reverse direction and still obey the laws of physics. But why is it that what we observe in nature does not appear to follow this pattern? Indeed, we know that there are things that can happen only in one direction in time, but not in the other. Nature is not time symmetric. Time is irreversible and irreplaceable. But today we will explore whether this is really so. The Nature of Time by Jayant V. Narlikar explores the possible reasons why time is purely constrained in the positive direction, despite it behaving like space in most other aspects. In our presentation today, we will explore 2 of these 3 reasons which Narlikar showed, which are the cosmological and the electromagnetic reason. The first example is the cosmological reason for time's arrow. It's long been observed that light from distant galaxies has been redshifted by the time it reaches us. And this shows that galaxies are actually moving apart from each other, and therefore the universe is expanding as time moves on. But what if tomorrow you woke up and saw the universe do this? What would this imply about the arrow of time? We would still expect to be able to distinguish yesterday from tomorrow that happened, which makes us question, does the expansion of the universe really give time its arrow, or does time's arrow come from something more fundamental? Let's keep this in mind as we explore some other examples that Narlikar has showed us. Narlikar also argues for an electromagnetic reason for the direction of time. It has been observed that an oscillating charged particle will emit electromagnetic waves over time and slow down. We, however, do not observe charges absorbing energy from infinity away and becoming more energetic, even though the laws of physics do not explicitly forbid this. If we did observe a particle doing this, would it mean that the particle is moving back in time? Let us consider a third case for the arrow of time, the thermodynamic reason for the arrow of time. Carlo Rovelli claimed in The Order of Time that the only reason we can discern the arrow of time through entropy is merely due to our labeling of objects and phenomena. However, from the second law of thermodynamics, we know that the entropy of a closed system can only remain constant or increase over time. We would never expect water to spontaneously gather itself up from the dirt and collect into a cup. Indeed, in every movie that depicts time moving backwards, they always show these entropy decreasing sequences. Entropy is fundamentally connected to our notion of time. If we ever saw a spilled cup of water, put itself back together, we actually might have reason to believe that we are moving backwards in time. Looking back at the examples given to us by Narlikar and Rovelli, we are left even more confused about what gives time its arrow than we were when we started. Indeed, we recognize that time is very intrinsically and fundamentally connected to the very nature of our universe. Yet, it seems more and more obscure the more we try to understand its nature and cause. Of the 3 examples, we opine that if there were one concrete example to explain the arrow of time, it would have to be the second law of thermodynamics.
We have come to the end of our presentation. If you would like to find out more about this equation, please like this video and follow our channel and subscribe for more options in the future.